Okay. So, how does the network processor architecture look like? So, this we have taken an example of actually 4240, they call it as a communications processor. So, whatever we had discussed, okay, you will see some parts of it inside this, because whatever the architecture we have seen is we are looking at this network processors interconnected by a switch, but what goes inside each network processor is something like this. Okay. So, the first functionality that we need is the frame manager. Okay. So, when a data packet comes through a 1 gig or a 10 gig port, okay, so you have to now take this data packet and then look at the frames, parse it, okay, classify the frames and then distribute. If you remember, if the data packet comes in one of these ports and then goes into one of these ports, we told that we need not look into the top level layer, but we can always, that was the architecture, right, we looked at the architecture in the previous slide. Okay. So, we send through this port alone, but if this goes into one of the ports here, okay, what happens is that you have to take the data, put it in some place, say memory or something, and then transmit the data packet to this place. Okay. And that is why you have these kind of say, and the second thing that you see in this network process is the buffer manager. Okay. We called it as a traffic manager in that slide, previous slide. Okay. The third thing you have is the queue manager, okay, because you can have priority, various priorities for queues. So, you have the queue manager here, and then you have security engines. Okay. This is essentially for encryption and other things, okay, and this is separate from your networking part, because this is common. I mean, if I take the data packets from here, it can go into the security and then return back. So, this is common to all these things. So, something like this. So, if you look at this, these are some of the parts of a network processor, okay, for one for frame acceleration and all that, and then they also have some extra acceleration. See, other than this, you have the regular processing stuff, I mean L2 cache, L1 cache and all those things, PowerPC architecture and all those things. This is the normal what you see in your regular general purpose process. The only thing extra is a kind of a fabric that interconnects these guys together. Okay. So, instead of a bus, you might use a switch. Okay. Bus, you have contention and all that. You can have a, I mean 16 cross 16 switch or something, okay, to communicate between these guys. Then the rest you have memory and all those things, which is normal. Okay. And then as I told you, the route processor has all these power management, security monitor and all those things. Okay. The only part that is related with networking is this, having a frame manager and then pattern match engine. So, that is actually the hardware. So, what they usually do is, instead of using software for parse algorithms and all that, they use these hardware accelerators. Okay. You have a frame manager, okay, which can go up to 50 gigabits per second, and it can parse, classify and distribute it to different ports. That is the speed that you can get out of this. The second is the buffer manager. Okay. You have 64 buffer pools. I mean, this is specific to this processor. If you take Cisco's routers, they manage about 64K queues, 64K queues. Okay. And then you have the queue manager. Here you have up to 22 power 24 queues, even in this. And then you have a rapid IO manager. Essentially, the idea is, see, this QR, these processors use, network processors use something known as data path acceleration architecture. Okay. Essentially, the idea behind this is, if I have a data going from one port to another port, I need not route it through the processor or the memory. I can just directly connect these two ports together and then route the data packets. Okay. So, that is managed by this. Then you have a security engine, and it operates at 40 gigabits per second. It supports IPsec, SSL, public keys, and then 1024 bits RSA. Okay. And then you have a pattern matching engine, which can operate at around 10 gigabits. See, all these are hardware rates. I mean, if you program it, you may not get this raw speed. These are raw speed. Okay. And then finally, a data compression engine, okay, which can work at 20 Gbps. So, the idea here is, if you go back, the idea here is most of the operations that are done by general purpose process are taken over by these accelerators, okay, and they have special hardware for doing this kind of job. Okay. That is the difference, major difference between your general purpose processor and a network processor. Okay. And this is exactly what we saw, I mean what goes inside this. Okay. So, now let us look at security aspects of this network process. Okay. So, Vasan would have talked about trust zone, but it is not applicable to network process. Any idea why? Any idea why? Okay, I think I leave it as a question to you. Okay. So, why trust zone is not applicable in network process? Okay. But other than that, secure boot feature can be used. Okay. So, for secure boot, I think high availability, I mean high assurance boot, we have discussed it, right. Then as we discussed, cryptographic accelerators, these are some of the important accelerators. So, it supports like something like symmetric and asymmetric keys, and then hash and all those things, SHA and all those things. Okay. And then a random number generator, which is very important for cryptography. Okay. Then I mean you can have secure storage. Obviously, this is needed to ensure that at least your processor is protected. But as I told you, there are attacks that can happen outside the processor. How we protect it is use good network architecture and things like that. Okay, one of the things in any protocol is the real time clock. Many of the protocols actually sync based on clocks. Okay, so you need a real time clock, and then they also put some security features like firewalls. Okay, say control access from CPU to DME and peripherals to, that is internal firewalls within the processor. Okay. So, then these are secure debug and then tamper proof and all that. I think Vasan would have discussed it. Okay. Anyway, so trust zone is not a part of this, and find out why. Okay. So, this is overall architecture of a network processor. Okay. And the instructionless states will correspond to whatever hardware accelerators you have. So, they will supply a bunch of libraries which you have to use to invoke these hardware accelerators. Okay. Now, so any question, and I mean let us break for 2 minutes, and any questions until now. So in this session we actually understood about what is networking and why packet processing is important, why switching is important, and then we also looked at the growth of the history of network process, okay, why network process came into existence, okay, and then we also looked at a brief architecture of a network processor. See, there are many companies that make network process. What we gave is one example. Intel actually makes some process. Okay, yeah.
Cost-wise, NP may be cheaper than the ASIC, but performance-wise, ASIC provides better.
See, the point is ASICs essentially performance-wise they are expensive first. Okay. Yes, performance wise, yes, definitely any ASIC will perform much better than a general purpose stuff. Yes, yes. So, but only thing is in high speed routers, okay, actually they concentrate. I will tell you why ASICs are used only in switching, because the point is that when you have to move data from one network processor to another network processor, okay, the processors have to process at that speed, and the data has to be routed at that speed. We will see that when we come to performance. Okay. Any questions from other places? Okay. So, if there are no questions, we will just proceed. Okay. Okay. Now, we are seeing about network processor architecture. Now, let us come to the important aspects of security. Okay. So, we saw that security, there were 7 levels of security or layers. Okay. So, at the data layer, yes, you can have cryptography, you can have trust zone, you can have secure boot, etc., protect the memory and all those things. Of the application layer, yes, you have cryptography that is used, and then you have applications like firewalls and all those things. But what is the protection for a host? What is the protection for an internal network? For example, someone clogs your port. Okay, that means send junk data packets, so that your port reads and it I mean once it reads and drops, but then it is reading, that is the point. Okay. Then what do you, if you connect it as a network, how do you provide perimeter security, how do you provide physical security, how do you provide policies? Okay. We will not be able to answer all these questions with network process, but at least we should be able to answer some of these questions. Okay. Now, with security, why do we have hardware accelerators? That is because you have, the problem is that you have to have fast data processing. We will look at performance, then we will understand why we need separate hardware accelerators for all these things. Okay. See, number of packets that a router can get can go into petabits per second, okay, petabits, and then number of drop packets should be more or less 0, because if any drop packets, it has to be retransmitted by top level protocols and things like that. There are a lot of complications in protocols. Now, in a hardware to packet processing, okay, so for this is what a router does actually. If this on the left hand side, you see, look at this, this is a bunch of ingress features that has to be given in a router. That is, once the data packet enters to a particular port, these are all some of the things that has to be done. I mean, there are about 33 operations that they have identified, like, so some of this include IOS, IPS, I mean packet inspection, and then ACL access control list check and so on. There are so many operations that have been done at the input port. Then the process of routing is more or less very easy. It has only 3 operations. On the egress, you have so many operations. Okay. So now, why I can't do ASICs for this? Because I need programmability. The first part of it is I need programmability. I mean, because I have to do so many activities, and the protocol keeps changing, because protocol is changed by IETF. IETF, if any company goes with a request, they will put a committee, and if the committee approves it, they will just change it. Then you need programmability for your processes. If you go with ASICs, what is going to happen? Okay. So, that is one of the reasons why they are not going with ASICs. They go with network process, because these operations can be programmed. Okay. Now, let us look at this hardware. Okay. So, we had seen how the router design happens, how now look at this. This is the, if you look at the real hardware, the high speed router ASR 9000 which you saw, look at this, these are all the network processes. Okay. The blue color ones are the network process, and these are connected to the ports, these are all the ports. Okay. So, each processor can manage many ports. So, look at this. So, this at least has 3 lines in this case. Similarly, I can have so each one of this is attached to a fabric interface ASIC. As I told you, this part of it is exchanging data from, so that you can move the data packets from this network processor and then go into some operations and then go back into another port. So, in this case, if you look at this, a data packet will come via this port, then it is processed by a network processor, then it goes into a fabric interface ASIC, then it goes into the arbiter or whatever it is, it makes a routing decision, then it again comes via this packets, okay, it has to go back in this direction. Okay. So, if you look at this, the amount of data that comes in, let us assume that even one of this is 10 gig port. Suppose I have 4 ports connected together, then the total is 40 gig, and you always design for maximum performance. So, 40 gigs going into FIA and 40 gigs also coming into this port, then switching has to happen at that speed, and then the data packets has to be traversed. So, the components that include here, okay. So, here you have a route processor, or it is also known as a route switch processor, which is a general purpose CPU, and then here is a network process, okay, and then here is the ASIC, which is a crossbar switch. Sometimes they use crossbar, sometimes they use Banyan networks and so on. There are many technologies for this switches. Okay. Now, usually this route switch processors, you can have a general purpose processor. So, usually X864 core 2.27 gigahertz is actually used in 9000 processors, which is actually normal that you find in your server boards. Okay. But one of the things you should see is the switch fabric bandwidth. Okay, that runs into 220 gig and so on. Okay. So, the switching is the one which actually is, now this is all data from field data, not theoretical data. Okay. Now, route switch processor, how does it look like? Okay. So, this is general. Now, even here you can have more than one CPU because of the data speeds. Okay. You can have more than one CPU. Then these are all the regular CPU complex, whatever the most important thing is the timing. Okay. And then they use for internally communicating here, they use something known as Ethernet out of band channel, okay, for communicating here. And then you have a this fabric interface ASIC for arbitration and connection. Okay. So, this is the route switch processor, so called, so this part of it. Okay. So, this is a general ASIC. Now, what happens to the fabric, switching fabric? So, if you look at this, the data comes from an ingress line card. Okay. Remember, once it enters an ingress line card, then there are 30 operations that I showed you, that has to be done by the network processor. After it is done, then it is sent to a ASIC. Now, this is where I use the crossbar switch, okay, just for performance, and that is why these routers are pretty expensive. Okay. So, for example, one of the routers can go up to 12 line cards, and the line cards can now each can have minimum, even if you consider 16 ports per line card operating at 1 gigahertz, 1 gigabit per second, then you can calculate it 1 into 16 into 12, that is the speed, and this has to switch at that speed. Okay. So, what happens here is, so they have something known as a route switch processor. So, if you look at the fabric bandwidth, okay, so if you look at this is a approximate numbers that they are given, okay, 8 into 5, 55 gigabits per second. Okay. So, per slot it is 440 gigabits per second, that is the kind of switching speed that you need. And remember, all these switching speeds are based on the clock frequency, and clock frequency proportional to power. Okay. So, that is where it takes lot of power. In fact, some of these high end routers take about 2 kilowatts of power. Okay. So, if you look at this here, it is 8 into 55 Gbps, that gets switched, and then the output also should be at 8 into 55 Gbps. Okay. This is one architecture of a router. Here is the other architecture where you have 5 banks. Okay. So, for bidirectional it carries up to 550 Gbps. So, that is why, I mean, this is supported today, I mean, this is slightly old slide. So, it was supported 2 years back, now this has increased, they have 7 layers and all that, this is only 5 layer switching interface. Okay. Now, this is the component, I mean the line card architecture. Okay. So, each line card that we are talking about, okay, so it has got physical interfaces and it can go up to 100 gigabits speed. Okay. And then the CPU can be used for control plane and then control plane operations. Okay. And then the network process essentially uses a forward and a feature engine. Okay. So, this is a highly integrated silicon as opposed to discrete components. So, it is all done in it is a core, okay, let us call it as a core. Okay. And then the fabric interface ASICs, which actually forms the interface between this network process and the CPU. So, this is the overall configuration of a router for performance. Okay. So, here is ASR 9000 router. Okay. So, here is an example of how they are all interconnected. Okay. So, if you look at this, in this case, for example, this is a normal CPU. Okay. So, here it has a 92 gig interface, whereas with the line cards and other place it has got a 440 gig interface. Okay. So, in general, okay, this is the way it's architectured. Okay. A router is high speed router is architectured. Each line card has a route processor, okay, and is connected to, see the switches can also be of different levels. Okay. We saw 7 layer switches, and you can have line cards of 7 layer switches, that is a current CRS architecture. Okay. This is the latest architecture of Cisco, this is how it is. So, essentially the idea is the back end, the back plane has more switching elements, and that increases the speed. Okay. So, on the ingress side you have so much of processing to be done, on the outgress side you have a bunch of processing to be done, and these are connected via these kind of switching interfaces. See, now the current trend is that you put the memory, the CPU, the NPU together, okay, and they act as small cells, okay, and all these cells are interconnected via these high speed switches. So that each network processor itself can manage more than, I mean, number of packets, and that is how you get increase in speed. Okay. So the architecture was actually very simple. Okay. So what we saw was that, one, we looked at the packet processor design. Okay. We saw that both for routing and switching, you have to take the packet inside, do certain operations, then do a forwarding and then send it to other packets, and this is the basic operation in any router or a switch. And the most important aspect of this is, and we saw the history where we found out that from a general purpose CPU, how we moved into a network process. Okay. And then we found out that the interconnect design was very important, and because of which they moved into ASICs. They couldn't, I mean, they didn't want to design network processor in ASICs because the protocols change, the way you process change, and because of that, if you go for ASICs, then you have to replace every time the protocol or the processor changes. Therefore, they just went for interconnect design alone with ASICs, and this was also good because you had to have that much speed for switching between one line card to another line card, whatever packets you are getting. Okay. Other than this, you had to have support for security. So the network processors by themselves supported lot of encryption, and I mean, they had accelerators for supporting encryption and other operations. We saw that there are different kinds of operations for frame handling and all that. Then for security in network operating systems, you have high availability boot, I mean high available boot and all those things. And then as far as performance is concerned, you have to have route process, network process and high speed ASICs, which can increase the performance. So as far as the processor architecture is designed, I mean, for networks are concerned, it uses massive parallelism and pipelining. Okay. Why pipelining? Because the headers have to be removed one by one. I mean, you first look at the outer header, then look at the inner header and so on. So that can be sent through a pipeline. Again, you build the headers in the same way. So that can be looked at as a pipeline operation. Since there are many packets coming via many ports, that can be looked at as a parallel operation, and your process must provide ability to handle this kind of speeds. So I stop here. This is just an introductory part. Okay, there are a lot of details on how these switches are designed and all those things, but then those are all not needed in this current course. So the most important aspect is now security part of it, we see only one part, like giving encryption alone is one that is provided by the hardware. The rest of the security parts has to come via coding and then better network design and so on. Okay. So with that, I stop this lecture, and any questions, I will be happy to answer.
Physical tampering.
Yes, physical tampering can be a fact, but then there are methods to manage. See, mostly in networking, the problem is not physical tampering, it is the data that is going out that is getting captured. Okay. And then attacking the box such that it cannot perform any operation, like DOS attacks, delay of service attacks, because a network box, if it does not provide the service that is intended to provide, and what is the point in having a box. So most of the attacks happen, see, only after they penetrate a network, they penetrate a machine inside an organization. Let us be clear. Okay. So what is important is the security of the network and how to ensure that your device does not get compromised. Okay. If you have most of these things in ASICs, obviously no one can program it, so they can just only send data packets to it and then ensure that the device does not work. So the major factor here is denial of service and other attacks. All the other attacks, for example, buffer flow and overflow and all that occur at the application level. Once they find out that your application has weakness, then they attack it. So from a network point of view, from a network processor point of view, there is not much we can, I mean, you can do with security. You always trust the data packet and send it. If, for example, someone encrypts a data packet which has a worm, as far as the router is concerned, it gets another packet that it has to pass through. Okay. So unless you put some other mechanisms like firewall and things like that, which will poke into the packet, they call it as deep packet inspection and all those things. Okay. So anyhow, thanks for participating in this session on network process, security and performance. Okay. I hope it was useful. Thanks for participation.